This video was brought to you by GeneralPAC.com, making power systems intuitive, open, and free to everyone, everywhere. Consider subscribing and supporting through patreon.com/GeneralPAC. This is the mechanism for you to support us financially so we can continue making high-quality power system video tutorials. Our corporate sponsor for this topic is AllumiaX.com from Seattle, Washington. Contact them for industrial and commercial power system studies. Reflecting a line-to-line fault on the high voltage side. In this video, we will see how we can actually reflect a line-to-line fault current quantities which occur on the low voltage Y grounded side of the transformer, but reflect the same quantities on the high voltage delta side of the transformer. So let's first have a recap of our video, part 3C-1, in which we calculated the fault current values for line-to-line faults. For the line-to-line fault type, we found that the positive sequence current was equal to negative J 3.33 per unit. And also the negative sequence current was equal to positive J 3.33 per unit. And the zero sequence current equaled 0, which means there was no zero sequence current. That can be expressed as 3.3 angle negative 90 degrees and 3.33 angle positive 90 degrees respectively in polar form. It's also important to note the subscript. The lowercase indicates fault current on the low voltage side, while the uppercase will represent fault current on the high voltage side. We now proceed by reflecting these per unit current values on the high voltage side, and then we will multiply them with the appropriate base values to find the actual ampere quantities. So given that we have a DY1 or a DAB transformer connection, to determine the high voltage positive sequence quantities, we will shift the low voltage positive sequence component by plus 30 degrees, and that can be done by multiplying the low voltage fault current by a value of 1 angle plus 30 degrees. That gives us 3.33 at the angle of negative 60 degrees. In the same way, we will shift the negative sequence component by negative 30 degrees, and that can be done again by multiplying the low voltage fault current with a value of 1 angle negative 30 degrees. And again, that gives us a negative sequence current of 3.33 at the angle of positive 60 degrees. Now remember, for the zero sequence current, line-to-line faults are faults that are unsymmetrical in nature and are not connected to ground, which means that zero sequence current will not be able to flow from the ground into the fault. And that explains why we don't have zero sequence current on both the low voltage side as well as the high voltage side of the transformer. Therefore, zero sequence current is equal to 0. We need to use the base values to convert the per unit quantities to ampere quantities. However, since we are working on the high voltage side of the transformer, we divide the base value of power, which is 30 MVA, by the high voltage side of the voltage, which is 115 kV, to get a base value of 150.6 amperes. And then we just multiply out the per unit quantities with the base value to get the ampere in symmetrical component quantities. We get 501.5 amps at the angle of negative 60 degrees as the positive sequence current, and 501.5 amps at the angle of positive 60 degrees for negative sequence current. And then back to our familiar transformation equations. They can now be transformed to phase current quantities. Again, we would remove the zero sequence current from these equations since they are non-existent to simplify our calculations. These are the equations that we get. Now plugging in the value of A to be 1 at the angle of 120 degrees and A squared to be 1 at the angle of 240 degrees, and the positive and negative sequence components to be 501.5 amps at the angle of negative 60 and 501.5 amps at the angle of positive 60 degrees respectively, we get line A current, which equals 501.5 amps at the angle of 0 degrees. Line B current equals 1003 amps at the angle of 180 degrees, and line C current equals 501 amps at the angle of 0 degrees. Now these values line up very well with the current flow path on the high voltage side. The fault current on phase B is twice the fault current on phase A and phase C. We can say that the fault current coming from the source on line B gets distributed evenly between line A and line C, hence they are exactly half of line B current. It also leads us to the fact that a line-to-line fault on the Y side resembles a line-to-ground fault on the delta side because there are two small currents on phase A and C, which is the characteristic of a line-to-line fault, with the exception that zero sequence current is absent. Now, this characterization was found in the Blackburn's books. Furthermore, this type of characteristic also makes it difficult for relays to distinguish between the two types of fault currents. Even if we try to calculate the zero sequence current using line A, B, and C current quantities on the high voltage side, we'll still get zero. Because the zero sequence current is equal to 1/3 of line A plus line B plus line C current, and plugging those values in, which is 501 amps at the angle of 0 degrees, plus line B current of 1003 amps at the angle of 180 degrees, plus line C current of 501.5 amps at the angle of 0 degrees, and multiply by 1/3 gives us 0. Next, we will calculate the zero sequence voltage with our reflected sequence current component quantities. To do that, we go back to our faulted sequence network diagram for a line-to-line fault and apply KVL in each of the connected sequence networks. We can calculate that the positive sequence voltage by considering that the voltage of the positive sequence source 1 angle 0 degrees and the impedance of the source, which is J.05 per unit. The positive sequence voltage for a one line to ground fault is simply the source voltage minus the voltage drop across the positive sequence impedance. For the positive sequence voltage, we need to consider the reflected positive sequence current on the high voltage side, which is 3.33 angle minus 60 degrees. So our equation becomes the following. We get a value of 0.85 at the angle of negative 5.5 degrees and per unit. Similarly, the negative sequence voltage is the source voltage minus the voltage drop across the negative sequence impedance on the high voltage side. For the negative sequence current, we need to consider the reflected negative sequence current on the high voltage side, which is 3.33 angle positive 60 degrees, and our equation simply becomes the following. And we get a value of 0.1665 at the angle of 150 degrees in per unit. And again, zero sequence voltage will be 0 because zero sequence current was also 0. We need to set up a base value to convert per unit voltages quantities to actual line to ground voltage quantities. V base can therefore be taken as the following. Now multiplying the component with the base values, we get the values as shown below. The positive sequence voltage is equal to 57 kV at the angle of negative 5.5 degrees, and the negative sequence voltage is equal to 11.05 kV at the angle of negative 30 degrees. Our three transformation equation will then transform the sequence component to actual line to ground voltage quantities. Again, since the negative sequence component is non-existent, we can eliminate that directly from our equations. Plugging in the calculated sequence component's values, we get the following. We finally have the actual phase A to ground voltage quantities. VA is equal to 67.3 kV at the angle of minus 9.45 degrees. VB is equal to 48.52 kV at the angle of minus 133 degrees. And VC is equal to 57.1 kV at the angle of 125 degrees. For a line-to-line fault, we clearly see that the high voltage line A voltage is the one that is least depressed, while the high voltage line B and line C voltages are more depressed. Again, that is probably due to the fact that we have twice the amount of line current going through line B, which is coming from the source, and then it is equally distributed on line A and line C, returning back to the source. Now, this was a very complicated video tutorial, but I hope this video was useful, enlightening for students and professionals. Please subscribe and donate on patreon.com/GeneralPAC so we can continue making high quality power system video tutorials. Thank you.